Okay, today's note session is about simple machines. A simple machine is defined as a device that multiplies the user's force or changes the direction of that force to make your work easier. There are 6 types of simple machine. A lever, which is basically a stick that pivots on a fixed position called a fulcrum. A wheel and axle, which is a modified type of a lever. It's just a lever that moves in a 360 degrees. And a pulley, which is basically, again, a lever whose fulcrum is the pulley itself is the fulcrum of the lever, and the rope being the stick. Okay, so a lot of times scientists would say, well, technically there really aren't 6 types of simple machines. There's really the lever, and a modified form of that is the wheel and axle and the pulley. And then the other one is the inclined plane, okay, which is basically a ramp of some kind. And modified versions of the inclined plane are the wedge, which is a movable inclined plane, or a screw, which is an inclined plane wrapped around a cylinder. So let's take a look at each one of these and how they make work easier. So the inclined plane is used to easily change the height of an object. Instead of lifting a box from the ground up into a truck, for instance, we can just move it up the ramp. And you're taking it up a certain height by moving it with a force along a different angle or direction. Okay. Staircase is an example of an inclined plane, just a variation of that. And the wedge and the screw are related to the inclined plane. So a splitting wedge is basically 2 inclined planes put together and moving. And a wedge is used for cutting things and fastening things. So things that cut, like a plane or a pair of scissors or an axe, are usually a wedge. Okay, and things that fasten, like a staple, are considered a nail, are considered wedges. A saw, scissors, as I said. And even the end of a hypodermic needle is considered a wedge. A screw is also, as we said, an inclined plane wrapped around a cylinder. So the other kind of simple machine, the lever, is a stick that's used in a variety of ways. A wheel and axle is related to a lever because the wheel represents a 360-degree turn of a lever. And the pulley is related to the lever because it's a variation of the wheel and axle. So if the wheel and axle is a variation of the lever, then obviously the pulley too is a variation of the lever. So there are a couple parts of the lever that we need to be familiar with, okay? The effort force, that's the force that you are putting on the lever. The load, or the resistance force, that's the force that the lever applies to the object. And the fulcrum is the pivot point. So if we look at a seesaw, as you push down on the seesaw, you're putting effort force in. The fulcrum is the middle of the seesaw, the pivot point. And then the seesaw pushes up on the other person. So this is a lever, okay? Effort force here, resistance force here, fulcrum in the middle. So levers can be defined into 3 different classes. And the first class is the classic example of a first-class lever is the seesaw. The fulcrum is located in the middle between the effort force and the resistance force. And you can see why this is the classic example. I'm pushing down, the lever's pushing up, and the fulcrum's in the middle. This is a first-class lever, the seesaw. Some other examples of a first-class lever would be a pair of scissors. So I'm putting an effort here, and then the lever is putting force on paper or something on the material or something on this end with the fulcrum in the center. Or a pair of pliers, effort force here, resistance force here, fulcrum in the center. Now a second-class lever has the load or the resistance force in the center. And the easiest one to remember is the wheelbarrow. So here's my effort force. Here's my pivot, right? I have a load of dirt here and I take it to a place and then I dump the dirt out. So the wheel is actually the fulcrum, and the load, or the lever, is holding on to the load in here, or the resistance force is in the middle. So when the resistance force is in the middle, that's a second class lever. Another example is this nutcracker. Here's my effort force, here's my fulcrum, here's my resistance force. Third class lever has the effort in the middle, and any like swinging tool or sports equipment. So here I have, if I'm sweeping, I have my hands are here on the broom. The pivot point is the end of the broom, and the broom is putting some force here at the end. Okay, so we have fulcrum, effort in the middle, and then resistance. A classic example is a baseball bat. Right, you have your hands on the baseball bat, you're pivoting at the end of the bat that you're holding, and it hits the ball, so your effort's in the middle. Swinging this hammer, same thing, right? Here's the pivot, the fulcrum, here's the effort, here's the resistance. So tennis racket, same sort of idea as the baseball bat. So machines are useful because they can multiply our effort force. I place a force and the machine multiplies that force, okay? They don't do any more work. They may be able to give you more power because you can get the work done faster and easier, but you're still doing the same amount of work, whether you lift this child alone or if you use a lever to lift them, okay? So the work that you're doing is the same. It's just you're either changing the direction of the force or you're multiplying the force. So here on a lever, if this is the fulcrum, I can figure out, how much work I'm doing. Work output is equal to the resistance distance divided by the effort distance. So you can take the resistance distance is the distance from the fulcrum to where the resistance force is going. Effort distance is the distance from the fulcrum to where the effort's being put in. So this is your input work on this side of the machine. This is the machine's output work over here. So input work can be lost due to friction when you're using a machine. So how efficient a machine is a measure of how much the machine converts your work that you're putting in into useful output work. So to find the efficiency in a percentage, you take the work output divided by the work input times 100 to get a percentage. Okay, now notice we're taking two units that are the same and dividing them into one another. Work output would be in joules, work input would be in joules, and so when I multiply that by 100, my answer is in a percent with no unit. Okay, so if we take a look at these machines here, what kind of simple machine is this X? It's a lever, but it can also be a wedge. It has a cutting surface there. Can you see that? Here, this is a lever, right? And it's a third class lever, fulcrum, effort, resistance. The tack is a wedge. Here I have a screwdriver. A screwdriver is considered a wheel and axle, right? The screw is an inclined plane. The screw is a type of simple machine, what we can also call it an inclined plane. So on the test, you're going to have to be able to identify the kind of machine that it is, and also maybe even if it's a lever, like I did here, the class of lever that I have. So make sure that you can do that. All right, we'll be working on some simple machine problems in class and taking a look in our student activity at the two primary kinds of simple machines, the inclined plane and the lever, and taking a look at the differences between the two.